Okay, so today we are going to discuss section 14.7 about the extreme values and saddle points. So is it you can see these slides? Is it okay? Can someone confirm? Okay, I assume it is fine. Okay, so extreme values and saddle points. We start by defining, considering definitions. So the first one is this one, that if we are having a function of two variables, f of x, y, and this function is defined on a region R, and which contains this point. Okay, so you can consider it to be this function be a surface in 3 dimensions, and this is a point in the xy plane. Okay, so the region on which this function is defined, it contains the point AB. Okay, now the value of the function at this point, which is f of AB, is a local maximum, or it's a local maximum value uh, if the value of the function at AB remains equal to or greater than uh, the values of the function at all those points x and y for all domain points x and y in an open disk centered at AB. So if you consider it again, it's essentially saying that if you looking into an open disk which is centered at the point AB, and for all the points which are located in that open disk centered at AB, the value of the function at AB remains equal to or greater than the values of the function f at all the points within that disk. Okay, so and similarly, if we are having the other situation in which the value of the function at AB is in that case it's a local minimum, if and this is a local minimum of the f if the value of the function at AB remains less than or equal to for all the values of the function which are for the points which are located within that disk. Okay, which you are considering an open disk which is centered at AB. To give you what's the geometrical meanings of these two statements, what are the local maximum and the local minimum, we consider this, you can say this is a graph of a three-dimensional function. So you can say it's a surface plot. So here you are having, for instance, this is this blue circle, you can say it's a local disk, but of course this disk is a projection of a disk which is located in the xy plane. Okay, so you can consider this projected here, and this point here, the red one, you could say it is a local maximum because there is no greater value uh, nearby for the function f. So you can see that this is the maximum value because if you are located within this disk, there is no other point at which the function achieves the higher value. And likewise here at this point, this is a local maximum here because within that disk there is no other point for which the function achieves a higher value than this one. However, for the same surface, this point is a local minimum, as you can see, because there is no smaller value for the function, then this particular one, if you are considering all the points which are located within that disk. So when you are considering that disk, it means all the points which are included within that disk. So you can see that all the points of the surface which are located within that disk. So a local maximum occurs at a mountain peak, and a local minimum occurs at a valley low point. So consider that to be a valley low point, and consider that a mountain peak here. Okay, so this is a geometry of local maxima and minima. Okay. Here we are having an example of a function which appears as the figure 14.38 in your textbook, and this is a graph of the function. This one here is the cosine x, cosine y, and e raised to power minus x squared plus y squared square root. Okay, and this function has a maximum value of 1, which you can see from here as well. Okay, because the product of these two terms is the maximum value it can go is 1. Okay, so and this is if you can consider this one, this can be a number which can achieve a value of less than 1. Okay, and now you can see this function has a maximum value of 1 and a minimum value of about minus 0.067 on the square region, which is defined here. For this square region here, you are considering in the xy plane. So in the xy plane, this is a square region, and if you confine yourself in this square region, when the absolute value of x independent variable remains equal to or less than 3 pi by 2, so you are going in the x direction. If this is the positive direction of x, suppose here, so starting from 0 to 3 pi by 2, which is of course in radians, and it's likewise you are going from the origin in the negative direction of x, starting from 0 to minus 3 pi by 2, and likewise here, if y is increasing in this direction, so you are changing the y from 0 to 3 pi by 2 here and minus 3 pi by 2 here, so that the absolute value of y remains less than or equal to 3 pi by 2 radians. So this is the region in the xy plane you are considering, and if you plot this region within this region, plot this function three-dimensionally, you get the surface plot like here. Okay, and for this one, the maximum value for the function appears at the origin, which is a value of 1. And then there is a sharp, you can say, decline or descent of the function, or rapid increase. And there are these four, you can say, compressions. So you can see these slightly reddish color compressions within this surface. So these four compressions, they result in the minimum value of the function which this function can achieve. So of course these compressions are going below the plane, which is the xy plane. Okay, so the value of this function is less than 0. And of course, given that in the xy plane, the value of the function is 0. Okay, so it remains, that's why I say minus 0.067. Okay, so there is another example which is discussed, and here, well, it looks like the roof surface. So the roof of a house, for instance. Okay, so this roof surface is the plot of this particular function here. So z is equal to 1/2, and you see that there is absolute value of x absolute minus y absolute, and then absolute value again. So you see there are double absolute value of x, absolute value of minus y absolute value, then absolute value of minus x absolute minus y absolute. So this particular function, if this is the z-axis going in this way, and this is our x-axis, and this is y-axis, this results in the plot of this three-dimensional surface. Okay. Now this roof surface has a maximum value of 0. Okay. So here is the at the origin here, and a minimum value of minus a on the square region which is defined here. So the square region you can see is defined when x is absolute value of x remains equal to a or less than a. So it means that the distance from this point, the origin from here to here, is a, and the distance from here to here is a2, also a, and likewise this distance is a and this distance is a. So you are considering a square in the xy plane which has got the width and the length 2a. Okay. So, and the absolute value of x remains less than or equal to a if you are considering this square in the xy plane, and this over this square in the xy plane you get this roof surface, and the you can see a maximum value of 0 at the origin and a minimum value of minus a on the square region. So the minimum value, of course, occurring here at the end points here, these points. Okay, now there is the theorem 10, and it is about the first derivative test for the local extreme value. And it says that if function of two variables f of xy has a local maximum or minimum value at an interior point AB. So interior point of a domain you are considering, okay, in the xy plane, and an interior point AB of its domain, and if the first partial derivatives exist there, then both of these partial derivatives at the point A and B vanish. Okay, so we look at it again. So if you are having a function of two variables f of xy, and it has a local maximum or minimum value at an interior point A and B of its domain, and if the first partial derivative, if they exist there, then both of them vanish. So okay, so to see what it means geometrically, okay, so this statement, this theorem 10. So looking at this figure 14.41 in your textbook, so looking at that here, for instance, so this is the surface which is representing, which is plotting this function of two variables, f of xy. Okay, so this is our surface, the bluish one. So it's represent, this is the given one, z is equal to f of xy, and so when you are looking the partial, and this is the extremal point here, the point, the maximum, local maximum at this point here, where this little hand is here. So this is a local maximum. And now when you're looking at the partial derivatives, you know what the geometrical meaning of the partial derivative is. Because when you are partially differentiating this function with respect to x, it means that the y remains constant. And when y remains constant, it means you can imagine a plane which is parallel to the xz plane, and so y remains constant for that plane, and it's passing through that point. Okay, so and that plane will trace or will cross out a curve in and this is the bluish line is that curve. And this is which plane? A plane which is parallel to the xz plane. Okay, so this is the xz plane, a plane running parallel to that, but passing through that point. Okay, this is the point where the function achieves a maximum value. And now that particular plane will, you can say, cross out, or there is an intersection of this three-dimensional surface, the bluish one, with that plane, which you are considering. They will intersect with the bluish surface, and they generate this curve. This is the bluish curve here, this blue line. Okay. And now the geometrical meaning of the partial derivative is that the partial f over partial x is at that point local maxima. It is the slope of the tangent to that blue curve, which we obtain at the cross section of this plane parallel to the xz plane and crossing this three-dimensional surface. Okay, so this is then the slope of the tangent to that point here. And this tangent line at that point is represented by this red color line here. Likewise, if you now want to understand geometrically what is the meaning of partial derivative with respect to y, and when you consider partial derivative with respect to y, of course you are assuming x is constant. So for instance, this is the point if you project this point in the xy plane. So of course you get this point here, which with the coordinates a, b, and 0, and z coordinate is 0, of course. And now if you have got a plane which is you can consider this plane, okay, so which is running parallel to yz plane, okay. This is the yz plane, and this plane is consisting of plane formed by this line and this line, okay. And this plane is a plane for which x remains constant, okay, and x remains at a constant value of a for the plane defined by this line and this line. And the previous plane which we consider, which was defined by this line and this line, okay, and for that plane y remains at a constant value of b, okay, and for this plane defined by this line and this line, x remains constant at the value of a, okay. So now for when you have got the plane defined by x is equal to a, so this plane, okay, this plane defined by these two vertical lines, and now this plane intersects or cross out a curve from this three-dimensional surface, which is this curve here, okay, so this blue. And now these geometrical meaning of the partial derivative with respect to y here, it means the slope of the tangent to this curve, this bluish one, at this point here, and the tangent line is given by this red line, okay. So this is the tangent at this. You see these two tangents, this tangent line and this tangent line, and because they are at the same point, so if they themselves define a plane, these two tangent line, and this is the tangent plane to this surface at that point. Okay, so now you can see that if a local maximum of f occurs at point a, x is equal to a and y is equal to b, then the first partial derivatives of are both 0. So you see, if this is a local maximum here, and then it means that this is a peak point here. Okay, if this is a peak point, of course the tangent plane at this point will be parallel to the xy plane. And if that happens, it means that the both partial derivatives at this point must vanish. Okay, so this is a geometrical meaning of how there is a connection between finding the local maxima or minima and the vanishing of the two partial derivatives. Okay, now we come to the definition. An interior point of the domain of a function f of xy where both fx and fy are 0, or where one or both of fx these are the partial derivatives, where one or more f of x means partial f over partial x and f of y means partial f over partial y, where one or both of them do not exist is a critical point. So interior point of a domain of a function, so this is the two variable function here, where both of these partial derivatives are 0, or where one or both of them of these partial derivatives do not exist is a critical point. So this is the definition of a critical point. So either in a critical point, and either both the partial derivatives should vanish or one or both don't exist. So if this is the case, defines the critical point. Now there is another definition which is discussed, is saying that a differentiable function of two variables f of xy, it has a saddle point, which is another type of point at a critical point if in every open disk centered at a b there are domain points xy where the value of the function at xy remains greater than value of the function at ab, and the domain points xy where value of the function at xy remains less than the value of the function at ab. So you look at the situation here. So in the open disk you are looking into, there are domain points for which the value of function remains greater than this value. It means that this is a minima or minimum, okay, because the value of the function remains greater than that, okay, in that particular open disk. So at the same time, within that disk which you are looking into, there are domain points for which the value of the function for those points remain less than the value of the function at a and b. It means this is a local, you can say, maximum for the function. The corresponding point which you are looking into is, of course, has got the coordinates a, b. These are the x, y, and z coordinate is defined by the value of the function at a and b. On the surface is called, so this is the surface you are looking into, z is equal to f of xy, is called a saddle point of the surface. So essentially the idea in this statement is that in the same open disk, if you consider there will be some points in that uh, for which that particular point you are looking into a b, where the value of the function is the f of a b, it will be a maximum and for other points in the domain it will be a minimum. So this is a very interesting situation, and this is, for instance, happens in this sort of surface, in this kind of surface. So this is a saddle surface. Saddle, you can refer to the saddle when you ride a horse. So you sit here, so it's a surface generating, it's similarly looking. Now you see at this surface, you see that this point, this is a saddle surface because at this point here at the origin, if you consider it, you can say a region around that point here at the origin, okay, a region around that, and if you are going in the direction of the x-axis, okay, then this is a local maximum. So for instance, if you are here, so of course, if you are moving in the x-axis direction, the value of the function, it drops down, okay? So it's going downwards, okay? Whereas if you start from the same position here at the region and you are going along the y direction in this one, what happens is that the value of the function, it increases in both directions. You see, so it's a, in depending on which direction you go. Okay, so depending on which direction you go, in one direction or in one way, the value of the function is dropping. Okay, and in the other direction, starting from the same position, the value of the function, it is increasing. So it is, the surface is rising in some direction and dropping in other direction. So if that is the case, this is generates a surface called a saddle surface or a saddle. So this is a example of that surface. So, and this is the equation which generates that surface. Z is equal to y square minus y raised to power 4 minus x square. Okay, so the saddle point in this case is at the origin here. Okay, now we look at the example 1, which is about finding the local extreme value of this two variable function. So f of xy, x square plus y square minus 4y plus 9. Now, for this one, the domain of the function is the entire plane, so there are no boundary points. And this function can be defined for the entire plane. For any values of x and y, the function can be defined, so the domain is the entire plane. And the partial derivatives of this function, which you can easily find out by which are 2x is the partial derivative of with respect to x, and this is the partial derivative with respect to y, f of y here. So 2y minus 4, okay? Therefore, the local extreme values can occur only where, so these exist everywhere. You can see the partial derivatives exist everywhere. They can be defined for all values of x and y. Therefore, the local extreme values can occur where these partial derivatives vanish. This was which we just considered before. So to determine the local extreme values, what you do, you equate these two partial derivatives to zeros. So f of x is equal to 2x, which is 0, and f of y is equal to 2y minus 4, which is 0. Okay. And the only possibility when both of them are zeros, okay, and which is the point for which both of them vanish. And then of course 2x is equal to 0, it means x is equal to 0, and here it's a 2y minus 4 is equal to 0, it means y is equal to 2. You solve this equation where the value of f is 5. So at 0 and 2, the value of the function you just obtain by putting x is equal to 0, y is equal to 2, you get 5 from here. And since the f of xy can also be written, as you can see that this function here, as you can see, this function can also be written in this form, okay, x square plus, if you expand this square, and then there is a factor, there is a 4 that will appear in the expansion of this square, which will add up to 5, generate 5, and this term which comes from here, okay, minus 4y. And so this one, as you can see, it is square plus 5. So this value of the function, it is never less than 5, okay, because the maximum value that these two can, well, the minimum value these two parts can obtain is 0. So in that case, the minimum of this function is 5. So the function is never less than 5. We see that the critical point so this point is a local minimum, okay, because the function is never less than 5. Okay, so now this is the graph of the function, this function here, x square plus y square minus 4y plus 9. So if you plot this function in 3 dimensions, you get this surface plot. So z is here and x and y Then this is the graph of the function f of xy, x squared plus y squared minus 4y plus 9 is a paraboloid. So this is a paraboloid which has a local minimum value of 5 at the point 0 and 2. So you consider where is the 0 and 2. So x is 0 and so this is the point here 0 and 2. Okay, so this is the point. It has got a local minimum and the minimum value is 5 for this paraboloid surface. Okay. Now this is an example of a saddle surface, and this is the graph of this equation. Z is equal to y square minus x square. You can again see this is a saddle because if you see that a plane which is the xz plane, okay, and if you consider the xz plane intersecting or crossing this surface, it will generate out this curve, okay, this yellowish looking curve. Now if you consider another plane which is the yz plane, okay, this will cross out this curve, the blue curve from this surface. Okay, so the surface is you can say descending in one direction and ascending in the other direction. It is rising in one direction and going down or going down in the other direction. So this is the case we consider, and this is the property of the saddle surface, and this is a example of a saddle surface, and this is generated by this particular equation. Okay, now this is the figure 14.44 in your textbook, and this is again the same surface which we just looked at, y square minus x square, but this one, these red lines are the level curves. Okay, but these level curves are when the, for instance, this is 3 here, it means when the value of the function is 3. So if you look back again, so if you, it means that if you have got a plane which is intersecting with this three-dimensional surface, and that plane is parallel to the xy plane and at a distance of 3 units above the xy plane, okay, and and then that plane will intersect with this saddle surface and will generate these lines, this line and this line. Okay, so this is when, so this is a level curve when so these number 3 and 3 means that the f value of the function at is here is 3 and 3, and so this is a level curve. So you are again defining the value of the function 1 at these lines. Okay, so this is another representation of a three-dimensional surface by plotting these level curves and then putting numbers, so deciding which curve this is generated by which level of the plane which is intersecting with the surface parallel to the xy plane. So the origin is a saddle point of this function, as we have just seen. Okay, and there are no local extreme values. You can see that this is not a local extreme value because the function is rising in one direction and is going down in the other direction. So there are no local extreme values. So these are the level curve for the function which we just looked at previously. Okay, and now there is a theorem 11, and this is the theorem which describes the second derivative test for the local extreme values. Suppose this is a two variable function and its which is f of xy, and its first and the second partial derivatives are continuous throughout a disk which is centered at a b, and that the partial derivatives of f of x and at a b, partial derivative of f with respect to y at a b are both vanishing. In that case, the theorem states that f has a local maximum at this point A and B if the double partial derivative of f with respect to x, so this is a double partial derivative of f with respect to x, remains or is less than 0, okay, and the product of these partial derivatives, so this is the second partial derivative of f with respect to x, and this is second partial derivative of f with respect to y, minus this is again the partial derivative x and y. So first you differentiate partially with respect to y, then x, then square it, okay. So this term calculated at a and a b point here, it is bigger than 0, okay. And similarly, so this is the condition which mathematically describes the local maximum at this point, okay. If this condition is satisfied, it means that the function has got a local maximum at this point. Now the function has a local minimum at this point if again the second partial derivative of f with respect to x is greater than 0, and again this whole expression, it remains greater than 0 at the same point, okay. You see, in these two conditions this expression remains greater than 0, whereas only is the change of the sign of the second partial derivative with respect to x of the function f, they are changing the sign, and this change of the sign means whether we are having a maximum or a minimum, okay. And f has a saddle point at the point a and b if this term which we just consider here, so this is the same term, it remains less than 0, or it is less than 0 at a and at the point a b. So here in these two situations you see that this remains bigger than 0, and here it has now become less than 0, and this results in the saddle point. And the test is inconclusive at a b if this term here, it vanishes at the same point a and b. In this case, we must find some other way to determine the behavior of f at that point a and b. So this is a theorem which describes the second derivative test for determining the local extreme values. Okay, and we now look into that this expression which is given here. Okay, this expression here, f second partial with respect to x and the second partial with respect to y minus xy second partial x partial y and then square of that. This thing, this is called discriminant. This term is called the discriminant or Hessian of this function. It is sometimes easier to remember it in the determinant form. You can put this expression as a determinant of this determinant. As you know how to calculate this determinant, you multiply these terms together and subtract the product of these two terms. Okay, what you get is this. So this is the Hessian or the discriminant for this function of two variables, and this Hessian or determinant discriminant or the Hessian determines whether we are having a local maximum, minimum, or a saddle point. Okay, so let's look at the example 3. So in the example 3, find the local extreme value of the function. This is a function of two variables. Okay, so this is a function is given here, and the function is defined and differentiable for all x and y, and its domain has no boundary points. So it's defined and differentiable for all x and y, as one can see here. Okay, and it has no boundary points, so it is defined and differentiable for everywhere. So the function therefore has extreme values only at the point where the partial derivatives are simultaneously 0. So what you need to find out the partial of f with respect to x and partial of f with respect to y. So you calculate the partial derivatives, you differentiate with respect to x, it gives you this expression, equate it to 0, and likewise you differentiate with respect to y and then equate it to 0. This generates this pair, which is x is equal to -2, y is equal to -2. Therefore, this point -2 and -2 is the only point where the f may take on an extreme value. So this is the only point where the function can take an extreme value according to the theorems which we have just looked at. And to see if it does so, we calculate a few quantities. The second partial derivative of f with respect to x at this point. Okay. So what you do, you differentiate this again, this function with respect to x, okay, which it gives you -2, okay, and likewise, so this one is here, and likewise if you differentiate this function here with respect to y again, it gives you -2, so it's here. And if you differentiate f x y, so basically you differentiate this one with respect to x, it gives you 1. Okay, as you can see, it's 1 here. So if you know these three quantities, then you can find out the discriminant of f at this point, AB. So AB point is -2 and -2. So you find calculate the discriminant, which is given by this quantity here, f xx f yy minus f of xy square. You put the values of x and y here. Okay, so these are the values of x and y which you are putting. This is the extremal point you are looking at. Okay, and then you get the value of the discriminant, and the value of the discriminant comes out to be 3. Now the combination that the f(xx) is less than 0 because it's given by -2, and also the discriminant is 3 and is greater than 0, tells us that f has got a local maximum at -2 and -2, because these two conditions, if you look at second partial derivative of f(xx) is less than 0 and the discriminant remains positive. So if you look back the condition, so it's here, this is less than 0 and this is greater than 0. So this is the first one condition, local maximum. So you conclude from here after this calculation that this has got a local maximum at this point, -2 and 2. And the value of the function at this point can be calculated to be, you just put into the function, this is your function, when you put x is equal to -2, y is equal to -2, you get 8. So this is the value of the function. Okay, here is the summary of the max minimum test which we have looked into. Excuse me, yeah. So the extreme value of this two variable function can occur only at the boundary points of the domain of f. So when you consider a domain, the extreme value can occur at the boundary points, the outer edges, okay, or the second possibility is the extreme value occur at the critical points, which are the interior points where the partial derivatives disappear, or the points where the partial derivatives with respect to x and y, they fail to exist. So the critical points we define previously. What are the critical points where either the partial derivatives they vanish, or where the partial derivatives fail to exist. So there are two possibilities: either the extreme values occur at the boundary points or at the critical points. If the first and the second order partial derivatives of f are continuous throughout a disk which is centered at the point A and B, and this is the partial f defined at A and B, and partial f of y we defined at A and B are both vanishing. So the both partial derivatives calculated at A and B both are vanishing. The nature of f A and B can be tested with the second derivative test. Okay. So if there is these partial derivatives are continuous throughout the disk, and both the partial derivatives are vanishing at that point, okay, in that, what is the nature of the function at a and b, okay, whether it's which kind of extremal point is that, it can be, the nature can be obtained by the applying the second derivative test. And what this says, these are described by these conditions, that the of course we saw that the second partial with respect to x less than 0, and this discriminant should be greater than 0, okay, at the point, then in that case it's the local maximum. Second partial with respect to x greater than 0, and the discriminant is greater than 0 too, both of them, then this is a local minimum. And this discriminant, if it remains, if it is less than 0 at that same point, then it's a saddle point. And if discriminant is 0 at that point, then this test is inconclusive and you need further investigation. Okay. Now there are exercises 14.7, and I am going through these very quickly, okay? So for instance, the question number 1, 2, 3, 4, so the functions are given and the asking you finding the local extrema for these functions. So these are the functions, 4 functions, function of 2 variables, and your question is asking find all the local maximum, local minimum, and the saddle point of the function in the exercises, okay? And now for these 4 questions, I have just written down here and just have a capture of the, so here what you are doing for the question 1, for instance, finding the partial derivative with respect to x, partial derivative with respect to y, okay, and then if you solve this, then it gives you the critical point to be -3 and 3. You calculate the second partial derivative with respect to x, with second at the same point, -3 and 3. Second partial derivative with respect to y, and partial with x and y at the same point. You get the values of 2, 2, and 1. So this is the calculation for the discriminant, okay, which remains greater than 0, which is 3. So, and the second partial with respect to x is greater than 0, so it's a local minimum. Applying that condition, it gives you that it's a local minimum at that point, okay. Likewise, you can follow for the other question. So this one is another second function of 2 variables. You follow the same steps and it comes out to be that it's a local maximum at this point, okay. And likewise is the question 3 and 4. The functions are different, but the procedure is essentially same, okay. Now we go to the question 11, 12, and 13, okay. So the function of 2 variables are given here. There are 3 functions, okay. And then in 11, 12, and 13, so here are the solutions to those, and these are again following the finding the critical points, and then finding for instance, in this one, it's the application of again the finding the discriminant and finding whether they are which kind of local minima, maxima, or the saddle points they are. Okay. So if somebody has got any questions? If there are any questions, please let me know. Okay, so there are no questions. So we are now ending the meetings, and I will see you in the next meeting.